Hello.
Hello.
Yeah. So, can you hear me?
Yes, I can hear you.
One second. Right. So, your exam is in couple of days.
Wait. Just wait for a minute, okay?
Hello.
Hello.
Yes. What happened?
Yes, wait for 1 minute. He's joining.
Your voice is not clear.
Just wait. He is joining, okay?
Hello, sir.
Yeah. Hello.
Yeah, I can hear you. Sorry for the delay. I'm just setting up computer, all those kind of things.
Fine. Who is actually a student? You or
Oh yes, I'm the student. Yes.
you?
Hello. Yes,
You are the
I'm the
student,
student. Yes.
right? My voice is clear.
Yes, your voice is clear. Yes, very clear.
Oh yeah, great. So, your exam is coming in a couple of days.
Yes, next Tuesday actually. Early in the morning next Tuesday. Yeah, we have a exam, and I just want some help with a VHDL. Somebody to clear my mind a little bit to make sure that monitor me
How
to all
how
this
strong?
question.
How good are you in VHDL?
I won't say very good. I'll say okay. Okay. I won't call myself very good.
Very good.
So I know you probably very good. That's why I need your support to help me up my game.
Right. So, I mean, see, it is. I mean, I just want to know where you stand in digital design and VHDL programming basics. So that is why I'm asking
Okay.
you few questions. Like, how can you describe VHDL? I'm not asking you any abbreviation. Why you need VHDL? Can you define the need for VHDL?
It's basically entity, architecture and all those things, isn't it?
Yeah, right. Fine. So you're talking about the syntax, entity, architecture,
Yes.
port, and everything. That's fine. That's part of the program template and
Yeah.
architecture. I mean, VHDL is a program, right? There is no doubt about it. But why do you
Yeah.
need this? You need some reason for VHDL, right? Go code something in VHDL. Why do you need
I think
this?
I think it's to speed up the digital design because the logic is the conventional, the synchronous. It can take a lot of time, and I still remember that when I was in undergrad, I did like a project with deep flip flops, and then we just switch light with LEDs and then resistor, all those things. It require a lot of wiring and all those kind of things. But for VHDL, it's probably just a few lines of code, and then you probably can get a very beautiful output.
Yes, yeah, right. So I mean, it is a kind of simulation program for digital component, right? A kind of
Yes. Yeah.
software that you can use to simulate any digital component, and
Yep.
it saves a lot of time in designing digital system, right? You understand
Yep.
in that way? Yeah, fine.
Yep.
Yeah, right. So though maybe I think I don't know maybe where you stand. You know how to start from the VHDL code. I think the basics. I mean, let's say if I take a basic code of VHDL, let's talk about uh, VHDL logical gates.
Okay. Logic gate is
You
fine.
can see
AND
my
gate, OR
screen.
gate. I can see your screen. Google, yes, VHDL.
So yeah, that. But I think I want to know how well you understand the basic declaration stuff, starting from library and the architecture entity and everything. Why you need this, all that stuff from just to get something from your side. I mean, where you stand. I'm asking all this actually. So this is a basic code actually, right? For a AND gate. If you can see the screen, they have implemented AND gate, right? So let's start from this library IEEE. You know why we do this? Library IEEE.
The definition, right? It's the definition of the source. I mean,
Yes.
the whole thing.
Right. Okay. So use, I mean, yeah. So the next line is, I mean, IEEE.std_logical_1164.org. So what is that?
That is for, that is basically, I think it was a different kind of what software, I believe. They have a different iteration. They have 1984, they have 2008, they have all this kind of things. I think it's very important as well.
What will happen
so basically,
if I don't use this library?
You probably cannot run the program.
Yeah, we know that we cannot run the program, but where you exactly get the error actually if you don't include this line?
Syntax error?
Syntax error, yeah, you'll get that, but basically we include this library for IO kind of declaration stuff and definition. For example, you will be having a port declaration. Inside the port declaration, there will be a input, output, and every other stuff, right? So how do a program or a compiler knows that this A should be declared as input, B should be taken as output, and Y is output, something like that, right? Something related to input and output configuration. All these stuffs are defined in this library, std_logical_1164. So it is like when you do a C program, there are few input and output statements, right? Scanf and printf. And so for a compiler to understand the input statements, you need to include a library in the form of header file in C language. So sddio.h, right? In C. Have you heard about C language? C programming?
Yes, I have heard about C language. Yes.
So
I don't normally use C nowadays. Nowadays people use Python, sir, because Python.
Yeah, okay. So just a kind of library that we need to include so that the translator or interpreter, whatever, should be able to understand this input-output declaration part. That's it, right? So these
Understood.
2 lines are fixed. Then entity declaration. I mean, how can you define an entity?
Entity. So basically, entity is how do I put it? Entity is let me think. What is entity? Entity.
You are
Entity. Entity is like it's like wire and signals, isn't it? Basically, port and signal is like how you describe the thing, describe the object.
It is not describing about the function of the gate actually. It is more about focusing on the structure of the gate. If you see the entity, inside the entity, there will be a declaration that actually gives you how the gate will be. What are all the inputs? What is the output, right? So you will see a kind of non-functional structure of the gate. Actually, you are not going to understand the working of AND gate from the entity section, right? But you will understand how the gate will be structure, input output ports, how many inputs are there, how many outputs are there, and maybe if needed, if there is any clock signal for operating this component, everything will be something that you can understand from entity section, right? You understand, see here, there is a entity
Yeah.
section that actually describes about the port of the component. So it is a very simple statement, a simple word actually to describe about the entity. It gives you IO interfaces of a component, right? Make it simple. IO interface, input output interface of a component. It gives you that scope, right? Entity. That's why you
Yeah.
start from here. Entity and gate. And gate is actually a kind of variable name. You can name it any name you want, but entity is a keyword. IS is a keyword. Is also a keyword. There you start declaring or maybe defining the IO interfaces for the AND gate, right? So this
Yep.
case, in this program, uh, you are trying to construct two input AND gate, right? Can you see that port? And there is a bracket. A is the, what is A? A is an input, right? A colon in std underscore logic. Why we mention this std underscore logic? Standard logic. What is that standard logic?
Yeah. It's a syntax, isn't it? Standard logic. You have
It
to
is
write
a
this way, otherwise it's
syntax,
wrong.
but it says that A can be either 0 or 1. The value should be in the logic level. Value cannot be
Yeah.
cannot be analog. It has to be a digital value, right? std underscore logic. Input A is the input, and the value of A should be in the logic level, either 0 or 1, right? Right? Maybe the
Next time they have something, a vector standard logic vector, so from 31 bits to 0,
it is there. We will discuss that.
Maybe we can design an ALU, arithmetic logic unit. So it's all, calculator.
You already know this, right? But still, I think we need to know why we are doing this. We can, right. That's very important. So you are designing two inputs AND gate and then one input OR gate, right? See, one input AND gate. Sorry, one output. There is one output, right? So that's it. Do we have anything apart from this? Because you are not operating on IZ, right? Where you require VCC, ground, or other stuff. It is not about designing IZ. You are taking one gate from the IZ and trying to emulate its operation using VHDL, right? That's what you are trying to do here. And that is why there are only two inputs and one output, right? This is entity. This entity is something that you can maybe extend for the remaining gates also, not only for the gates, for any combinational circuits like decoder, encoder, multiplexer, demultiplexer, or maybe sequential circuits like flip-flops or SD flip-flop, JK, T flip-flop. So many components are there, right? So now, hello?
Yes, I'm still here.
Now, actually, let's talk about flip-flop. So if I'm focusing only on entity. Let's talk about flip-flop. So if I'm designing flip-flop, what do you think will be the change that we need to make in entity section? Flip-flops, let's say D flip-flop. There is a D flip-flop.
Yeah, I think there will be a clock, isn't it? And then there will be input and output. So it's like
clock should be there. Yeah. Clock is an input.
Clock is there.
Clock is an input.
I believe it's input.
Right. What about other stuff? Let's say D flip-flop. You know about D flip-flop, right?
Yeah. So there probably will be D. There'll be clock. And
D clock.
Probably then input standard logic.
Sorry.
And then there will be a Q. Yeah, a D, and then you dot clock, and then you do all those things, and then just input int standard logic quotation mark.
That's fine.
And then
only two inputs for D flip-flop.
Yeah, there's two inputs for D flip-flop. There's one input for D, and then
there is also another input actually. I think you know about it. Reset is also there, right?
Yes, the result is also there. There's the reset.
Maybe some external input where if you can apply reset, it will automatically make it 0. Q, right?
Oh,
understand?
Yes.
Some
reset.
Few other additional inputs also there, right?
So outputs so there will be.
Outputs are Q on Q bar.
you talk about is synchronous and asynchronous reset. So this is a different ballgame, you know. I'm just talking about the basics.
No, it is not that we will not have reset signal for synchronous circuit. There is also a possibility that we may have to include reset pin or reset signal for
flip-flop.
synchronous also. In some
Okay.
cases, you might need that for your application. There is no fixed stuff, like only in synchronous stuff you will have a reset, nothing like that actually. Let's say if in case there is an uncontrollable error, okay. So, but the clock is still running. But what you need is you need some external signal to completely reset the flip-flop. Even see you are working in synchronous flip-flop sequential cycle. So in that case, you need an external reset pin also actually to control the synchronous circuit. Hello?
Yeah, I'm still here, sir. I'm listening.
Yes. So this is about the entity. You need to structure your digital component, and then about the architecture. How can you define an architecture?
Architecture is basically like, you know, A and B, right? Y equals to that. So you have to, like, you know, begin.
So what you're
to
trying to do here, you have all the expressions, stuff, and everything inside the architecture. So what it is doing, what the architecture is doing actually. The entity is actually
you want to
giving you the structure of the digital component, whereas the architecture is
you describe the architecture.
Architecture is giving you the functionality of the component, right? How a component should work. In this case, the component should and A and B input, right? Put the result in Y. So it is the operation. It is always about the operation for architecture, right? How can you implement the operation of a digital component? All these details should be included inside the architecture, right? Whereas the entity is about the structure, right? You understand this?
Yes.
So these two sections should be there in almost all the design of digital component using VHDL, right? Now, I think you have sent
some practice problems, you know.
I think you have sent some sample stuff, right? Practice problem. Have you worked on this before?
Not yet, sir.
Do you think you can handle those?
Do you think we can what?
Once again. So here is the. Can you see this? This is right. This one, right?
Yes.
It starts from here. Do you understand? I mean, I think you look okay with this programming stuff, but I just, I mean, it just
can we, sir, professor, sorry, sir, doctor, can we just talk a little bit about, you know, flip-flops, latches, and register? Can we, for this class, can we just, no, how about this? Can we do a little bit of modeling? Can we do a little bit about structural modeling, data flow modeling, and behavioral modeling? I'm just a little bit, you know, quite bad at this kind of modeling stuff. Can you just like clear my mind a little bit? Because I think the basic is fine.
How good are you in understanding the concept of flip-flops and the digital components? Do you know the working of these flip-flops? I mean,
do you want to do the do you want to do modeling first? Maybe we'll do a bit of a data flow, structural modeling, and different kind of behavioral modeling. Maybe we can, you know, I think I know all those, you know, sometimes component and this kind of thing. Sometimes I get mixed up. Maybe you can, you know, clear my mind a little bit about this. I think that would be a very good idea. And then, or you want to do a register or shift register and all those kind of things, or flip-flops. We can do those things as well. Which one do you think we should focus on first?
I mean, see, I think you don't need to know internal working of the flip-flop. I think you have to be good enough to understand what are all the inputs and output if you take any digital component. Let's say if it is RS flip-flop, you know how it is working, right? Let's say if it is, let's say R equal to 0, S equal to 0, what happened to the output? Do you know at least to that level?
You mean for flip-flops? D flip-flop?
Yeah. Let's say I talk about RS flip-flop. You know RS flip-flop?
Yes, so I think so, yes. But
Right.
it depends on which gate are you referring to, right? As latch. Is it like a set reset or NOR latch or
No.
SI?
Let's not focus on that. Okay. I think maybe we'll get into that maybe when we design using VHDL. Let's focus on this actually. So you actually want to know the differences between data flow modeling, behavior modeling, and structural modeling, right?
Yeah, yes.
So see, the implementation is one second. Let's start from this actually. Uh, uh, Behavior modeling.
Okay. Sometimes process component, all those kind of things. Sometimes they get mixed up, because I'm still like upcoming, sometimes.
One second. Right. In most of the time, we'll be discussing about, we'll be designing VHDL system using behavior modeling, but structure modeling is also a kind of concept where we can use it in complex system digital design, I think. Okay, let's start
Okay.
from behavior modeling, actually. See,
Okay.
you don't need to worry about, what to say, uh, mm, let's say,
Data flow, and structure too much. Is it? I just need to focus on behavior.
wait. So the main difference between behavior and data flow modeling is you can compare. You know the difference between interpreter and compiler.
Okay.
What is the interpreter and compiler?
What is
The difference.
what is what?
You know what is the interpreter?
Interpreter and comparator.
So
Hello, I can't hear you, sir.
I think there is an issue with this internet connection. So in behavior kind of modeling, each and every statement or an instruction are executed sequentially, one by one, line by line. Hello, and hello, can you hear
Yes.
me? Right?
Yes, I can hear you.
It is not exact 100% of what you're trying to do with the digital component. Because behavior style is not something that you see in real life. If you design a circuit, let's say AND gate using wires or power supplies and everything, right? You have the lab, go there, take a small chip of AND gates, and give a power supply, ground it, or give all the wire connection. Finally, what you do, you will see the operation of AND gate, right? By giving different inputs at the input side, right? 0, 0, 0, 1, 1, 0, 1, 1, right? Hello.
Yeah.
This actually, when you switch on the power, when you switch on the supply, what actually happen? Will the circuit, each component of the circuit work sequentially or concurrently?
I think concurrently, isn't it?
Concurrently, right? I mean, you see the changes. You cannot describe that in time also, actually, not even in nanosecond. So it works parallelly, right? But in behavior model, it is not the case. See here, behavior style consists of one or more process statement. Sequential statements are executed sequentially by the simulator. The same as sequence of sequence. Okay, this. Whereas this data flow modeling is different, actually. Data flow description consists of one or more concurrent signal assignment statements. See here. Hello. There is a difference between data flow and behavior. In the data flow, in both the cases, the entity is same. Because the entity is not going to differ, right? The structure is always going to be same. But in case of data flow model, you describe the operation using a default operator. See here, sum equal to A XOR B. I mean, we are talking about off adder. Carry equal to A and B. You know about off adder, right? Hello?
Yep.
You
Yep,
know
I
about
do.
the off adder, right? So this
Yeah,
case,
the value we set is under the entity, it's basically the wires, the port. What's the signal, the wire, the port, all those things. Yes, A and B, and then that's the logic we want is the sum and carry out. Yeah, this half adder. Yeah, you need to know the
this,
logic
right?
gates very
Entity,
well.
you understand the entity of
Yeah.
off adder? Entity of adder is, I mean, obviously it should have two inputs and two outputs, right? One is in the form of sum, the other one is in the form of carry out, right? See, this entity section is common for all the modeling, actually. You see, behavior modeling is same. Structure style is also same. The only thing is how we implement the function for each off adder is different. In case of data flow modeling, I mean, you focus more on how the data will flow from one gate to another gate, actually. I mean, it is a kind of, you visualize the data flow between the gates, actually, and how you can represent that in coding is what they have done inside the architecture. So yes, sum equal to A XOR B, right? That's how it does it, actually. I mean, when you do a XOR operation of A and B, you'll get sum. Yes or not? You'll get sum. And the carry out operation is an AND operation of A and B. This XOR and AND operations are already defined in VHDL. They know how to do it, actually. So this is happening. This is happening with the data flow model. But if you can compare the same operation with the behavior model, it is a little different. See here, you are actually trying to use all the data that you have to implement the order off adder. For example, in case of behavior modeling, the execution takes place only if you change the inputs. See here, there is a function called process. Can you see? Process, right? This is actually
yes. Okay, why do we put process here? Hello, yes.
That is very simple, I think. See, you don't want to execute the code always. I mean, see, we know that the entity is always there, but AND operation, you want to perform AND operation only if there is an input, right? Hello. I mean, let's say initially one guy came and he actually input A equal to 0, B equal to 0, right? When so he is giving A equal to 0, B equal to 0. I mean, is trying to change the input, right? Whenever he is changing the input, the control automatically goes to the process function, right? Goes to the function, and inside the process function, all inside the process function, there will be some VHDL instructions, right? That will be getting executed. So this happens only when you try to change the input, because process takes two arguments. One is A, the another one is B. You understand these two? Process takes two arguments, A and B. So you are trying to inform the compiler or interpreter of VHDL, whatever. Only if there is any change in A and B, come and execute this function under process. Otherwise, don't execute it. You understand? It is a kind of, waiting for event, actually. Waiting for the event. What is that event here? When you change any inputs, that is actually an event. When that event happens, you should come and execute that code. You understand this process function stuff? Hello? Hello?
So process is basically how I can think about it is basically is they make the sequence happen. So it's like a sequence statement, you know. So it's like process. So we have a process, so process A and B, and then we begin something. So we begin when A equals to 1.
That is fine. That is fine. But when this process will be executed, that's what I'm asking. This process will be executed only if there is any change in A and B, right? Let's say,
okay, yeah.
You understand? That's what I'm trying to say. That's what I'm trying to say. If there is no change in A and B, is there a need to execute the process? No, right? Hello?
No. Yes, understood.
No, right? Yeah, that's what I'm trying to say here. But in case of data flow modeling, this will be always executed, right? Hello? When I give an input, this will be always executed. But this whatever you see here, process begins, right? If A equal to 1, then sum equal to not B, carry out equal to B. All these stuff will be executed only if there is any change in A and B. Hello, you got the point?
Yep, I'm still here. Yes, I'm still here.
Right. So you see the difference here. I mean, data flow modeling is all about using your already defined operation like XOR and all will be defined in a library. You just need to make use of that library and make sure that how the data is flowed, right, from input to output. Whereas in this case, you are trying to define the XOR. See here, there is no XOR operator. Yeah. Can you see in this behavior model? You are trying to define the behavior. You are trying to define the behavior whereas here the behavior is already defined in the form of XOR and AND gate. You just go there and get the already defined behavior and make use of that behavior in your design. I mean, in designing off adder, right? But here you are not using any XOR gate or not gate or whatever, right? You are trying to, you have a Boolean expression. You have an expression for sum. You have an expression for the carry out. You try to these expression with the help of assignment operator or not operator and try to get that job. That's what you're trying to do here. Can you see here? Hello?
Yes.
Right?
Absolutely.
I think let's talk about the truth table. Sum and carry, right? You know what is off adder? 0, 0 means? You know this?
Oh yes. This is basically one is the NOR is another one is X NOR and another one is N. Yes.
Yes. Now how can you define this actually in terms of Boolean expression? How can you define this?
So basically you have two outputs. So if you have a half added, so if a sum and then carry, so S is equals to A bar B plus AB bar.
That is fine, but we are not doing that in behavior model. We are doing that in data flow model. So using AX.
Data flow.
Right.
Okay.
But what we do here is, if you see this, if A equal to 1, then sum will not be. Carry out equal to B. See, if A equal to 1, here is A, right? If
Yeah.
there are two cases where you see A equal to 1. If A equal to 1, then sum equal to not B.
Oh, I see. I can see how this coming. Yeah.
See here, sum equal to
Yep.
not
I
B.
saw that.
Sum
I saw
equal
that.
to
I saw
not
that.
B, right?
Yep. Oh, that's behavior. Oh, A equals to 1, and then sum. Okay, carry equals to B. Oh, okay, and then vice versa.
Carry, whereas carry equal to B, carry out equal to B. If you see this, A equal to 1 means carry is B actually, right? Whereas sum is not
Carry
B.
is.
Sum is not B.
Yep.
Because sum, see, B equal to 0. So not B equal to 1, right? Carry is B. So B equal to 0. So as B equal to 0, carry is 0. You understand this?
Yep.
Right? Hello? I think a kind of
Yeah, I'm
shortcut
still
to
here.
this, right? Whereas if this is fine, else means what? If A equal to 0, right? If A equal to 1, this else means what? There is another condition, that is A equal to 0. If A equal to 0 means sum equal to B. Yes, you are right. Right? Sum equal to B, right?
Yep.
Hello?
Yep, you're right.
See? Right? A equal to 0 means sum equal to B only. Right? Whereas carry equal to carry is always
Carry.
0.
Yep. Carry is always
Right?
0.
If A equal to 1, yeah, carry is always 0. See, if A equal to 0, it doesn't matter. Carry is always 0. Right?
Yeah.
If A equal to 1, sum equal to B bar, right? And carry equal to B, right? Hello? What you are trying to do here, you are defining the behavior. This is how it should be, it should behave actually, right? We can easily do this with the help of XOR gate and AND gate, right? XOR is what actually, what you are trying to do now, you are defining the behavior of XOR gate. You are defining the behavior of off adder actually. You are not using the already defined function, that is the XOR and AND gate. You go inside the truth table and you analyze the truth table, and then with the help of logical values, you somehow make the adjustment and make sure that your final output arrives, right? Hello? You understand what I said?
Yep.
Right?
Understood,
Whereas,
yes.
this is something that this is a kind of modeling where you go and synthesize the circuit. Maybe I can use this word. Synthesize means what actually? You take each part of the circuit and analyze what is happening with each section of the circuit in case of behavior style. Whereas in case of normal data flow style, actually, you already know the expression. You already have a gates for the expression. Just make use of that gate. Simple, right? Hello? Understand what I said?
Yes, I'm still here. Yeah, and I understood, yes.
Right. So what you can understand from this is data flow modeling is very simple. It is very simple because you are already using defined gates to implement the function, but we cannot use it for any undefined complex circuit. For example, you know that undefined complex circuit. For example, let's say I have this truth table. My truth table is this actually. I mean, you know, after seeing this truth table, you know that this is actually for off adder, right? Hello? This is actually for off adder. But let's say I have some random truth table. I have some random truth table. 0 means let's say 0 1 means 1 0 means again 0. So this is my expression. I can define it in any way I want. 1 means make it 0 again. Now can you tell me, can you define this with the help of any gates? Is it matching with any gate truth table? This one? No. Is it matching with any truth table? Can you define
Not
this
really.
using data flow model? I don't think so. Data
I
flow
don't think so,
style,
no.
because you cannot use any gates, right? You understand what I say?
Yeah.
right? See, let's say if it is like this, if it is like this, easily I can go for XOR gate, right? Yes or not?
Yep.
A XOR B, right? I'm done.
Yep.
Right? I can use data flow style, easily done, right? But in case
Yep,
of
yep.
this, you have no option, right? You need to,
No option. Yes.
yeah, you have no option. You need to go for this behavior style, right? Hello? Understand what I
Yes,
said?
I'm still here.
You need to go for this actually. How can you do this in behavior style? It is very simple. How can you do this? Can you tell me?
So basically, you have a process A and B.
Right, then?
If
Yeah,
A,
simple. I mean, you need to go for, what to say, lengthy stuff process, A and B, fine. Maybe if you can come up with a simple solution, that is also fine. Begin, then then tell
to
me
begin, and then if
if
if A equals to 0,
okay,
am I correct or I'm wrong? If A equals to 0, then
right. Go ahead then.
then if A equals to 0,
Right. I'll do it actually. If A equal to 1, it doesn't matter. If it doesn't matter, I don't need to worry about y. Y is always 0. Right? Can I do this?
oh, okay. Oh yeah, you
Right?
can
Can
do
I
that.
do
Yeah, you
this?
can do that.
This works, right?
Yep,
This
yep,
works.
yep.
Okay, now for this actually. What about A equal to 1? You cannot define it. Yes or not? You cannot
Yep.
define it. Can you define it? No, right?
No.
So what you can do for this? You don't have any other option. What you can do? You don't have any other
Just
option.
and if
That's it,
Oops.
right? You have to go for this. Yes or not? Right?
Yep.
Then
Y equals to 0, right?
right?
Oh, okay. So you do the stupid way. Okay.
Else,
Yes. Also, else.
Y1. That's it. You don't need to check another condition. Else Y1, right?
Oh,
No?
oh. I believe you need a semicolon over there. You know, semicolon.
That's
Probably not the
fine.
last one. But
Syntax error. That's fine. That's fine.
yeah.
This one, right? Right?
Yep.
Then and it. End process. Will
Yep.
this work? Do you think will this work?
I think so. I
Yes,
think
it
it
will
might.
work. But
Huh?
maybe you can think of a better idea also for this actually. So what you are trying to do here, that's the point actually. You are not focusing on what to say trying to get a gate for this truth table, right? What you are trying to do now, you get into the truth table and understand the behavior of the circuit. So right, that's
Yep.
what, right? That is the Boolean expression. Maybe you can do that also, maybe in the data flow model. This can be represented like this, right? In Boolean expression, A bar dot B, right? Hello,
Yep. Yep. Yep.
right? So this is what? This is actually behavior model, whereas data model, it should be like this, right? Hello, that's it. You're done. Yeah, yes or not? You're done, right?
Yep.
A bar dot B. See, this is the expression you want, right? Hello. I mean, let me copy this
No.
code.
Yeah.
Actually,
Yep.
right? This one, right? I mean, you don't need any if statement or something like that. In case of data flow model, just one expression will do, right? Yes. But
Yep. Yep.
you need to use already defined gates, right? Not A. This is not
Yep.
and B is equal to 1. Remaining 0, right? Hello?
Yep.
Right.
Yep.
Yeah, you understand this expression? This is for data
Yep.
flow. Whereas this is behavior.
Yep.
Right? I mean, see, if, structure, I don't know, we'll structure, maybe we'll discuss. I don't want to confuse you. We'll keep this for our later part, actually. I want to take more examples for data flow and behavior model. Make sure that we understand these two first. Then we'll introduce structure modeling. Right? Hello? Wait.
I understood. I understood. Yeah.
So this one is actually for first one, I think a behavior model description. What you're trying to do now, you are trying to implement NAND gate. You know what is NAND gate, right? Right?
Yes.
Right. So you know the truth table, right? A, B, and Y, or maybe C.
Yep.
In this case, 0, 0 is
Okay.
what?
NAND 1.
Right. Remaining.
NAND gate, isn't it? Yeah. Vice versa. Yeah. Those kinds of things. Yes. Yes.
Right. Right. So
Wait,
what you're trying
zero,
what
zero, zero, yeah.
right?
Yep.
So again, what you're trying to do here in the behavior model, you start from process, fine. And then if A equal to 1, B equal to 1, then C equal to 0.
Yep.
Yes, and I think this is not NAND gate. Correct me if I'm wrong.
This is NAND gate. This is
not
NAND gate.
NAND gate.
This is NAND gate, sir. This is NAND gate. You got confused now.
I mean, I'm seeing the code. Code is wrong, right?
You
If
see,
A equal to
it's not
1,
very
B,
rigorous, huh?
yeah. But for the remaining is, yeah, right. I think my truth table is wrong, right? Perfect.
Wait.
Yeah.
NAND gate. Yeah, your truth table is wrong, sir.
Right. This is fine, right?
1, 0.
Now what you're
Yeah,
trying to
now it's
do,
fine.
now what you're trying to do on the left side is you are defining each row of the truth table. If A equal to 1, B equal to 1, C equal to 0, right? This case you are taking. For the remaining case, it is always 1. I don't need to check the input combination. Can you see here? If A equal to 1,
Yep.
B equal to 1, C equal to 0, right? That is the only condition where you get output 0. For the remaining condition, the output is 1, always 1. So I don't need to check for A equal to 1 or B equal to 1. I don't need to check for the combination. C is always 0 for the remaining combination. So what you are trying to do now, you are trying to dictate the behavior of the NAND gate, actually, right? You are not trying to use the NAND gate that is already defined in the library of VHDL file. Whereas in case of data flow model, see you are making use of this actually. Can you see here? A
Yep.
and B and C, right?
Yeah.
I mean, if let's say in case of data flow model, it will be like this. C will be very simple, NAND B, right? Or C can be represented as what? Not A and B, right?
A and B, yes.
So both the cases, you can use any one expression if you want to design the same NAND gate using data flow model, right? You are already using the you are using the already defined function, right? You don't know.
So can we
See,
can we can we take a break? Can we have a break?
right? What?
5 minutes? Can we have a break? 3 minutes?
Yeah.
Or maybe
Yeah.
something I want to
Maybe we can
thank.
start. We can start after 5 minutes, 5 to 10 minutes.
Yeah. Thank you. 5 minutes. 5 minutes. Thank you. Sir, do you want to continue? So are you still here or what? Hello? Can you hear me?
Hello.
Yeah, let's continue now.
Right. So you understand the difference here, right? You don't need to what to say completely see operation of the uh, by actually defining any gates in case of behavior modeling. See here, you see the truth table and design the circuit according to it. That's it. So that is, I mean, in case of behavior modeling, in case if you are coming across any complex circuit that is not defined, that
Okay.
is what I mean not defined is what I mean not defined is this truth table is not defined. Right? This is not defined anywhere, right? This is not defined, right?
Yep.
So you cannot use any NAND gate or NOT gate for this describing this operation actually from this truth table. So in this case, it is always enter into behavior model, right? Hello? You understand? So
Yep.
maybe
Yep.
you need to understand. I mean, you need to be very selective actually. Where you can go for data flow representation, or where you can go for behavior stuff actually, right? Hello. Maybe.
Okay. Yes.
Yeah. Maybe we can see a sample question here. I think let's start from the basic questions. Sorry. Have you ever tried working on this? Actually? That is the question. This one, right?
Yep.
1 second. Please. Here is the first question. Do you understand
Yep.
this? Yeah, DD flip flop.
If
It
you
is not
want-
hello. It is not a D flip
Yes.
flop. It is a DD flip flop. A different one actually. There is a difference. A DD flip flop
Oh, right.
is a similar to D flip flop. It is similar, but it is not a DD flip flop. It is not a normal D flip flop. Except that
Okay.
flip flop can change the state on both the rising edge and falling edge. So this is very important. You know what is a rising and falling edge, right?
Yes, absolutely.
Right. So in case of a normal flip flop, the state of the flip flop changes only during either a rising edge or during either falling edge, not on both the times, right? But in
Yep.
case of this design, you need to design the flip flop which actually should work on both rising edge and falling edge of the clock, right? This is the first condition, right? So the
Yep.
first
Yep.
one is this. FF should work on both edge of the clock input, right? Right.
Yep.
Next, the flip flop has a direct reset input. I told you, right? It has clock, but apart from that, it also has reset. When R equal to 0, your Q must be 0, irrespective of your previous state.
Yep.
Right. So this is also
Yeah.
implemented. This you won't see this in a normal flip flop design. Then when S equal to 1, Q should be 1. Again, the same. Irrespective of your previous state and the clock input. Right? Hello?
Yes, I'm still here. I'm still here.
Yeah. I mean this, let me put it in simple. Without clock. right?
Yep.
You don't need to apply a clock. I mean, ignore, I mean, how to define it? Not clock condition is don't care. If you are, whether you apply a clock or not, it doesn't matter,
Okay.
right? It doesn't matter, but this design should implement this actually. So you need to write a code for this actually. So what about the truth table for this? What do you think will be the truth table for this? So D should be there, clock should be there,
Yep. Yep.
D should be there, clock should be there. There should be
And then
S input, there should be an R input,
SB. Yep.
right?
And
So
then there will be a Q output.
Q, right? So maybe I will start from this.
Okay.
Or yes, and then D and clock and D. This will be clock and if this is let's say if it is 0, you don't need to worry about the other condition, right? Right?
Yep. 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 Yep.
It is always 0, right?
Yes, absolutely.
So when it is 1, you need to check for this. If this is 1, don't worry about the clock or the input. Output is always 1, right? Yes, because S is equal to 1, right? Right? When this is 1 and this is 0, this is where you should listen to the clock. You understand what I say? When R equal to
Yep.
1, you are not going to apply a reset. When S equal to 0, you don't want to set. Now you are going to listen for the clock. Let's say clock is 1, right? I mean, it should work for both positive and negative falling edge, right? So you don't need, I mean, you should apply a clock. Maybe it can be 0 or 1, right? 0 means what? Falling edge, right? 1 to
Falling
0,
edge, yes.
falling edge. 1 to 0, falling edge,
Yeah.
right? 1 to 0, falling edge. 0 to 1, rising edge.
Rising edge.
Let's say I come from 1 to 0, falling edge. It should work. When D equal to 1, output equal to 1, right? And normal stuff, right? This is how D flip-flop works. Now, let's say 1, 1, 0. Now clock is on positive edge. Again, it should work,
Yep.
right?
Yep.
Right. Let's say if it is 0, it should be 0. Again, a negative edge.
Yep.
If it is 1, it should be 1. Now I'm going to copy
Yep.
this for this action. I mean, let's say I work on positive edge of the clock. Same result, right? You understand this?
Wait, let me digest a little bit. Yeah, yeah,
Wait,
yeah.
wait.
Okay.
I 1 to 0. That is falling edge. 1 to 0, falling edge.
Well, you can specify this in the code, or I need to write this in a very in a very you get what I'm saying, in this kind of manner. You get what I'm saying. Sometimes, what do you think? Do I have to specify like rising edge or falling edge or something? Or so I just straight away put output 1 0 1 0, or it should be, you get what I'm saying?
What did you say? You want you
If it's a rising edge, so basically 0 to 1. So should I just put 0, or I need to put like this?
And you need to do like
format.
this. Only then you will understand this,
Okay.
right? 1 to 0 means
Yeah.
it is a falling edge. 0 to 1 means it is clock doesn't maintain any state actually, right? I mean, for this design actually, you need to change the state of the clock for the flip-flop to work. If you want to activate the flip-flop, whether you should go from low to high, that is rising edge, or low high to low, that is falling edge, right? So it should be in the transition. That is why I use this, right? Hello? Yes.
Yeah, yeah,
So the first two condition is easy, right? You are not caring about the clock at all. You are not worrying about weight.
yeah,
Wait. Yes. You are not worrying about the clock at all for the first two calculation, the truth table, right? Because
yeah, yeah,
you try to change the value of R in the first case. So obviously the output should be 0. And then you are trying to set the flip-flop. This is to reset the flip-flop. This is to reset the flip-flop asynchronously, right? You should use this, right? Async,
yeah,
right? Because you are not expecting the clock to play the role here, right? Asynchronously. In this case, set the flip-flop asynchronously, right? Right? Understand this? No?
yeah, yeah, yeah. Wait, set it asynchronous. Yes, reset. Yeah, yeah, yeah.
But here is where you are trying to set the flip-flop using clock. So maybe sync, right? Synchronous, right?
Yeah,
Not set, this is reset. And this is set. Sync for using falling edge, right?
yep,
Now this, again the same, reset, FF, sync using rising, right? So we know this. Now, how are we going to design this using VHDL? Do you have any plan? Do you think, can you do this using VHDL? Hello?
wait, wait. I'm processing. I'm processing. So it's rising. Okay. So
Right?
now we have to obviously we need a code. Obviously we need entity.
Yeah, I
Right. We
think,
need
yeah, let's start from you actually. Let's start from entity,
yeah,
right? Maybe
yeah,
I have a syntax issues, so don't
yeah,
mind that. Okay. So
yeah,
now this is going to be my entity.
yeah.
I mean, let's start from here. So now this is going to be my DD flip-flop, not D flip-flop, right?
Yeah, so I can't see the complete things, I can't see the left. The things a bit. Oh no, I can. Okay, good.
Right?
Yeah,
Got
yeah, I'm
right?
good. I'm good.
You understand
Yeah,
this?
got yeah. Understand? Yeah. Wait, let me read it.
Entity is
Yeah,
perfect.
correct. Yeah, entity is perfect. Yeah, port clock. It's good. It's good. Out, and then there's a Q naught. There's two Q. Q and
Maybe
Q
if you
naught.
don't want Q naught, then maybe we can erase it.
Oh, really? We can read this. Is it important? Otherwise, it's wrong. Huh?
No. We don't need this because we are not using it
Okay.
in our case, right? In any case, right? We can do this. This is fine, right? Is this fine?
Okay. This
Right?
is fine. Yes, because this is
Now the
the
entity is
output.
done. What about the architecture? That's where, I mean, I'm going with architectural. I mean, I'm going with behavior model, right? Hello? I'm going with
Yeah.
behavior model because kind of truth
That's the
table
question.
this, you cannot use any data flow model here. I don't think you can use data flow here. So I go with this
Yep.
actually, behavior stuff. I mean,
Yep.
I already have a code, but I think I need to rework on it actually. This is not a proper code, right? I mean, DDF, right? So DD architecture, then DDF. Now, let's start from this actually. I'm going to erase this.
Okay.
Now let's start from begin. Now the process, right? Right?
Yep.
Begin. But before going into the process, I mean, let's focus on the process first. What are the input? Clock, then Then what?
Wait, let me process. Process.
Then D only.
Clock. D
Clock
only,
and D,
yes.
because these two inputs are something that goes with the clock signal, right? D should work with the clock signal. That is why I put that inside the process. If there is any change in the clock, I should come to this. If there is any change in the D input, I should come to this. But if there is any change in R and S, I don't need to come to this. I don't need to come to process.
Yep.
Right?
Yep.
We will take care of that maybe later on, R and S. We'll deal with that later on. But this is very important. Process. And now I am going to start the process. Then begin. Now what you need to do? I enter into the process. Now what you need to do? There is a change in the process. Now what you need to do? I should look for, I should consider these two, right? These four combinations.
Yeah.
I will be entering into the process only if R equal to 1, S equal to 0. So I'm entering here because if there is a chance that I'm entering here because there is a falling edge or rising edge occurred. Okay, so it comes inside the process. I mean, my control comes inside the process. If there is any change in falling edge clock, or if there is any transition in the clock signal. So now this works for both falling and rising edge. Okay, we should focus on this actually. The input begin Q equal to D. That's it. Hello. You understand this?
Oh yeah. Yep. You're right.
You are done with process actually. You are done with the process. End process.
Wait. Begin Q.
But what about R and S? But what about R and S? We need to focus on R and S also, right? Hello. If there is, where you define it?
Yep.
Where you define it? You can go. You got to use if statement or something like that. It cannot be inside the process, because whatever is inside the process should be executed after there is a change in the clock signal, right? But these two combination works without clock signal, right? Hello, should work without clock signal, right? I don't need to worry about the clock signal. But if there is if R equal to 0, I should make Q equal to 0, right?
Yes.
If R equal to 1 and S equal to 0, I should make Q equal to 1, right? Right? So
wait, this is not correct. If R equals to 1 and then S equals to 0, it can be 0, 1, 0, 1, you know? It can be changed, you know, depending on it's a rising edge or falling edge, or it's on a lot of things, you know? It's on a lot of things. It's depending
on. If R
on
equal to 0, why do you want to check clock signal and D input? This is what they say here in the requirement document. If you see there, if you read it, see here, the flip-flop has a direct reset input. R equal to 0 means reset the flip-flop to Q equal to 0. Simple, independent of the clock. Don't worry about the clock. Hello, understand?
Yeah, I'm here. Yeah, I'm reading. So let me think. Direct input,
similarly,
reset input.
Yeah. So do you want to change anything in the table? I think, is it looking perfect? No. What do you suggest?
Oh yes, it is. Oh, it is perfect. Yeah.
It is
pretty
perfect,
good.
Right?
Yeah.
Right. I'm giving reset the higher priority. That is why 0, it doesn't matter whether S equal to 0 or 1. Output should always be 0.
Yep.
Hello? Right? When R equal to 1, when R equal to 1, which means, I mean, compared to set input, I'm giving reset input the higher priority. If S equal to 1, you should make Q equal to 1. So how will you implement this actually? I mean, outside the process, it should come because it is not dependent on clock. So it should be if, then R equal to 0, there is no question.
Yeah.
Then that's it. Q
Q equals 0.
That's it, right? Done. right? This one,
Yep. Yep.
right? No question about it, right? Else means
Yep.
what
Yep. Yep.
combination might come. Maybe I can do like this, or maybe end if is also there.
Wait. So you don't move so
Yeah,
fast now. A little bit slower.
End if,
And NF, yes, NF.
right? Make it 0. That's it, done.
Yep.
If S equal to 1,
Then
then
wait, let me think. S equals to 1, then Q equals to 1.
done, right? So these two conditions should be executed first, but this will be executed always, these two, but this process function will be executed only if there is a change in clock and D input. You understand what I said? This will not be executed
Yep.
always, right? This will not be executed always. If there is only change in, if there is a change in clock, if there is a rising edge or falling edge, only then this will be executed, right? Right? Hello? You understand what I say?
Yeah.
Right? So you need to be careful with the code actually. You cannot put this code inside the process. Do you think you can? No. If
No, I
you
can't.
put
So I
this,
just separate out.
if you put this code inside the process, this code will be executed only if there is a change in clock signal. I don't want that, right? Hello? This code should be
Yes,
independent of clock. You understand the concept, right?
Understood.
So this is actually the solution for the first problem.
Oh, so basically, so when I'm dealing with this kind of question, let's go back to question now. The question that he was asking. So we have to read the question very carefully. We have to kind of technical question. We have to know, oh, this is D flip-flop. So what is D flip-flop? There's switch, set, reset, and have a clock, and have a D, and then a Q. And then we understand the concept. So it's once 0, XXX, and then the output will be 0, and then once it's 1, and then the set is 1, and then it will be cross, and then the Q will be high.
Okay. Which one? The second question?
The first one, and then we have to write 1 0, and then 1 0, and 1 0, and then it will be rising edge or falling edge, and then you will get a result. So in this kind of case, we just need to focusing on the clock, the D, and R and S. So basically, for this case, we need to first think about the clock. So the clock is obviously the rising edge or falling edge, but the Q will always follow the D. The Q will always follow the D. The Q will always follow the D.
You will always follow the D only when you actually, if there is any transition in the clock signal, right? I mean,
but so can I ask why under wait, can you go back a little bit? Can you go back to the answer? So 1 0 1 0. Okay, if why? So I think you made a mistake. We see 1 0, and then 1 0. Why it's always 1 0 1 0? It should be 1 0 1 1. It's not always.
Maybe we don't what? I think it has to be 1 0, right? Why? Let's say if it is 0 1, if it is 0, and if it is don't care. Okay. Now let's say this condition occurs.
You overcomplicate. Okay.
If this condition occurs, what should be your priority? Your R equal to 0, right? You should focus on resetting the flip-flop. Yes or not? Will you worry about this reading the status of clock, or you will go and reset the flip-flop if R equal to 0? Hello? You understand what I say? The reason why I put 1 0 here is in case if this becomes 0, you should not listen to the clock. Right? Should not listen to the clock, right?
You should always
because
listen
R
to
equal to 0. R equal to 0. See here, when R equal to 0 means it resets the flip-flop independent of the clock, right?
Yep.
Right? And that is why I see, that is why when this condition comes, only then process should be executed. I mean, R should be 1, S equal to 0. Only then you should listen to the clock. Yes or not? No?
Oh, okay. But so why is D changer? Why is D is 1 is 0 and then 1 is 1, 0 and 1?
I mean, it is just two combination. I mean, just a combination. Maybe you can simplify it like this actually. I'm just for your understanding. Maybe you can erase this. Maybe you can have like this. If this is your
So you see, you hear to me. So you just know you said set and reset. So if it's set, then set should be 1. So it should be 1 1, and then 1 0 is reset. So 0 is set, reset, and 1 is set. So that's why it's 1 0 1 1.
Let me simplify this truth table first once again. If
So
this
you
is
did
the
this
case,
is a very
this is the case, then Q equal to D. Hello? This is
okay.
Q equal to D, right?
Yeah.
Right? Hello? When you are giving D
Yes.
input, Q equal to D. So if you
Yeah.
simplify this, that's it. Only 4 columns will come, right? Right? Yes? Now fine. This is your falling edge. This is your right. D can be either 0 or 1. D can be either 0 or 1. But Q is going to be D. Yes or not? Hello?
Okay. Understood.
You understand this? Now,
yeah,
what is your doubt?
but sir, I'm just slow, so that's why I was like, you said set and reset. I just want to change the number based on set and reset. So I cannot think this way. I cannot think like, okay, set is low, so it's 1 0, and set is high, so it's 1 1. I can't think like this way. I have to follow the clock, and then with the clock, and then you have DNS, DNQ. So D always follow Q. I have to think like this way. So set and reset is irrelevant. It's not important in this point.
Is needed for these 2 cases, set and reset.
Oh, it's only needed for first 2 cases.
Yes. Yeah, you are right. I understand this. Set and reset is irrelevant for these cases. These
but
2
relevant.
cases. Yes.
But for the other 4 cases,
other
4 cases,
yeah,
other 4 cases is relevant.
You can simplify it to 2 cases. I mean, Q equal to D. It doesn't matter whether D equal to 0 or not. Q equal to D. Simple. Right? Yes or not? No?
Yeah. Just follow that, right? Q follow D. Yeah.
That's what we do here. Right?
Yeah.
Here in
Q follow D. Correct.
So that's why I simplified this. But this for this to happen, you need to have R equal to 1, S equal to 0. Only then you should return to the clock according to your requirement. Right?
Requirement. Yeah. The requirement should.
Yeah. R should be 1, Q
requirement.
equal to 0. If R equal to 0, then it should come to this. Right? Straight away, it should come to this. You should not listen to the clock. So your circuit should be designed in that way.
Okay.
There should be a comparator or maybe whatever to check if R equal to 1 or 0. If R equal to 0, then you don't need to be listening to the clock for the D flip-flop that's coming, right? The clock signal should not be listened. Should not listen to the clock. Right? So these 4 combinations should be employed. And this is what we have done in the code also, right? See here. This is for the first 2 row, and this is independent of clock. And this is for the second 2 row, right?
Understood.
End architecture. I mean, I don't know what is the keyword. End process, then we should end the architecture also.
Yeah, and architecture and DFF, DDFF, double D flip-flop. That's it.
Right? Something like this, right?
Yeah.
So this actually we have done this, but maybe you need to. Do you have any solutions? Do you have answer for this? All this? No, right?
I do have a solution for this, but sir, I don't want to show you the solution. I don't want you to rely on his solution. I want you to. We go through together. We go.
Do you understand that? Do you understand those solutions? If you can understand, no.
I don't want to show. I don't want to look at the solution. So it's not good. You look at the solution, you learn nothing.
Oh, you have a solution, but you haven't seen that.
I haven't seen that. I don't want to see the solution because I always feel like see solution, learn nothing.
Right. So what about the second question? What do you how will you define this?
Am I right, sir? You look at solution, you learn nothing.
No, what I will suggest you is maybe you try to, for example, I understand that you don't want to see the solution before giving any attempt. That's fine, but at least you could have given an attempt on question 1. If you can do that, maybe you know where you stuck, right? You will know where you stuck. So you need
Yep.
to clear all those barriers actually. For that, maybe you need to see solution at least few questions solution actually. I don't want you to see all the solutions actually. Maybe at least to cross the barriers, you need to see how they go about the process. I mean, maybe I
Understood.
don't know. I'm not sure. Let's say let's focus on this. Can you do question 2
Yeah.
so that I can see where you stuck?
A, B, and C. Okay, so
Can you do question
synchronous.
2? I mean, you
Yeah,
just need to
question two.
focus
Yeah,
on process. Can you do that? Can you do
yeah,
and
yeah,
send
yeah.
me? I have the
Yeah,
solution too.
wait, I'm doing it right now. Wait. Let me think.
Right.
Question 2. So okay, so the VHDL description synchronous should stay should below. Okay, so port A, B, and C.
Yeah, you need to focus on functionality.
Begin.
Process, we should start from process or maybe a process, I think.
Yep, it will be a process. You're correct. So process. So if process clock CORN Q is the output. What so there's no C, did he make a mistake?
Yeah.
I don't see any C, just saying. And my begin. So
Are you working on it?
yeah, I'm working on it. Yeah.
Right. Can you send me, I mean, just to know where you actually make a mistake or where you actually, maybe if we can do.
So I'm thinking, I'm thinking. Let me think. I'm
Right.
thinking how to construct the whole thing. So we'll be begin,
Okay.
and then process,
Mhm.
and
Process, then bracket. What are all the arguments?
yeah, I know. Process, process. There will be process. There will be clock. I assume clock and clock.
Yeah, clock.
CORN.
Yeah, clock.
Right.
COK.
COK and then COKRN. CORN is it?
You don't need that.
That's
Why
just
do
it.
you need
Oh, I
CLR?
don't need that.
Because your CLRN is independent of clock. Can you see the truth table? When CLRN is 0, output is 0, irrespective of
Oh, okay.
clock A and B, right?
So
So you
it's
don't need
the
to
beginning.
put that inside the process.
Okay. So it's a clock in the beginning, and then if I see the rising edge, so the rising edge
Mhm.
will
Clock
be
rising
output.
edge,
So the
comma A
yeah,
and B, comma A, comma B.
yeah,
3 arguments should be inside the process.
yeah. Or more than that. There were 4 arguments. They're like QT bar,
Why do you want
C,
QT bar? Okay, you do it and send me, I will see.
A. So the first two, is it a bar B plus a B bar? So it's like a NOR gate, Is it like a NOR gate?
Yeah, I think you should go for behavior model. I think this
Yeah,
is interesting. Let's see how you come up with a solution. Even I'm waiting to see that. I think it is not that difficult. You can do it. Straightforward, right? Hello?
Wait, so XNOR. No, it's an XOR gate. Sorry, XOR gate.
You don't
XOR gate.
you cannot use any gates for this actually. You should go for behavior model. You should use conditional statement like If
Condition statement.
yeah, if
Oh,
right. You
we
cannot
can
use
if
yeah. If A equal to B, A equal to 0, B equal to 0, then you should go with that kind of approach, I think. No? Yes. Yes, that's
wait,
how
let me
it
think.
works. Hello.
Yeah, so basically, so is it if A equals to 0, right? And if A equals to 0, then uh then
If A equal to 0
Q-
and B
uh,
equal to 0. If A equal to 0 and B equal to 0.
so I get what you're saying. So you want to use the stupid way. I'm thinking about, is there a smart way? Okay, and B equals to 0, and if then it's like QT plus 1 equals to QT.
I
Right.
think you don't have that kind of variable in your port declaration. You just have Q, right? Can you see entity port declaration? You have Q,
Oh
you
yeah.
don't have QT plus 1. So how will you do that? It is very simple. Q equal to Q. Your previous Q, your next Q is going to replace your previous Q. Simple. Hello? Q equal to Q.
Yeah, I'm still here, sir.
You understand? No?
Yeah, so it's a Q, right?
Yeah, Q, just Q. Q equal to Q. For A equal to 0, B equal to 0.
Oh,
For A equal to 0, B equal
okay.
to 1, Q equal to Q bar.
Oh, if A equals to 0 and B equals to 1, so Q is equals to Q bar. Okay.
Yeah, right. If A equal to 1, B
Oh, okay.
equal to 0, Q equal to C bar. C is
If
already
A
there, right?
equals to
It should be.
wait. B equals to 0, B equals to 0. Wait, let me think. So let me think.
Right,
Where did I make
right.
a mistake? Where did I make a mistake?
Yeah.
Q C bar. Ah, so if let me say this correct. If A equals to 1,
Mhm.
A is 1, and then and B equals to 1,
Mhm.
Q is equals to wait, Q is equals to B, isn't it?
Yes.
Hello.
Yes. Yeah, right.
So semicolon, and so the last condition is if A equals to
That's
if
it.
cross sure.
No, you should not have that. There is no cross. I mean, it is for our understanding the truth. VHDL cannot understand that.
I send you this, huh? I send you something. Wait. Well, I send you WhatsApp, and so basically, sir, but at the every if I need to end the if. So something like this, correct?
Can you send me?
WhatsApp. Yeah, WhatsApp. Something like this.
I think you can use this actually instead of if. Can you see the question 3? This makes sense, right?
Yeah.
B A equal to B want 1, C equal to or else maybe something like that as well.
So it's a check the WhatsApp. Yeah, it's
Right,
coming
right,
through. I believe
yeah.
it's right. Yeah, it's right. The guy very quick, very good, very responsive. Yeah.
Right, I'm checking it. I think this is fine. What about this condition? CLRN equal to 0. What do you want to do for that? That should come outside the process. That's it. Hello?
Yeah.
You should include a statement where you
Yeah.
need to
Wait.
use
So
if statement.
wait.
If CLRN equal to 0, then output is 0. You don't need to go inside the process. Hello?
Yeah. So basically, so what's gonna happen is that there'll be process. So I need to put something called end process. And then I have to another statement is that if CLRN equals 0, CLRN equals 0, then it's wait, if CI 0, then Q, right? Q equals 0. Basically something like that. I'll send you over WhatsApp. It's that's a statement I put.
So
This.
where is the code actually?
Is it something like this? That's what I wrote now.
Can you see this code?
Yes, I can see this code. Can you see my code now? Can you see the code I sent to you? Is WhatsApp. Over WhatsApp, I think he
Let me
sent you
check.
a message.
So you see this code, then you will see where you stuck. Maybe this will work actually. What is this? A equal to 1 and B equal to 1, Q equal to B bar. N process. Okay, so if CLRN is 0, yeah, this is quite straightforward, right? That's what I have done here. Here, see here, it starts from CLRN equal to 0. Right, yours is right. See here.
Oh, okay. Yes.
CLRN equal to 0, Q equal to 0. For the remaining stuff, I kept everything inside the process function, right? Same. It is not C, not B, then B, right? Yes.
Yep.
So this is how it works actually. The solution for your question too, right?
Yeah.
What about this actually? I mean, draw a circuit to implement the following VHDL statement. Interesting. I think we need to work on that. Let's focus on VHDL code. I mean, I'll come to question 3, but let's focus on this first. Let me focus on. I mean, there is one interesting part here.
Last one?
No. I mean, I don't want to confuse you with encoder stuff. Let's focus on multiplexer because multiplexer is one of the most frequently used component in digital design. So I'm going to focus on this question. The following circuit is S16:1 multiplexer built using 4:1 multiplexer. Write the VHDL code for 4:1 multiplexer and then 16:1 multiplexer using structure modeling, right? I'm going to see, we are going to discuss both the multiplexer design using behavior modeling first. Maybe next we will see the structure modeling. See, 4:1, you know what is multiplexer?
Yeah, but sir, he didn't specify which one you want to use, So you can use behavioral and then you can use structural. You can use both. You can use either one. I think because it didn't specify, so you can use whatever you want. And then the second one, he said he want to use structural modeling, so we'll use structural modeling for the second part. What do you reckon?
Yes, structural modeling. The reason why they ask us to use structural modeling is they want us to use 4:1 multiplexer to be a part of 16:1 multiplexer. That is why they ask us to use structural model, right? We can design 16:1 multiplexer separately, actually, without help of any other module, actually. But first, they ask us to design 4:1 multiplexer, right? We have 4:1 multiplexer in hand. Next, with the help of 4:1 multiplexer, you need to design 16:1 multiplexer. That is possible only with the help of structural modeling. Hello?
Yeah.
I'll explain you. I'll explain you some. I'll give you some example for structural modeling. Wait.
Okay.
I think we have seen. I think that is it. Right. Yes, gone.
So can you, I want to pee. I will be back 2 minutes. Thank you. Thank you.
Right.
So sorry for waiting.
Right.
Also, I'm back.
1 second.
This, I think, multiplexer requires a lot of signal, wires, port, signal, all those kind of things. It's not easy, This part is with the later part, the whole thing is gonna get a little bit more difficult. Multiplexers, I think, obviously
See,
there's standard logic.
I think it
61.
is.
So
I mean, yeah.
is it gonna be like 16 down to 1? We have to write something like that, and then we have the port map. We have to do all those things. I assume we have to do all those things.
Let's start from the basics. Actually, you don't want to go work on multiplexer straight away. That too, in structural model, you don't want to do that initially because it is a little complex circuit, right? Let's start from NAND gate. You know what is NAND gate, right? You know what is NAND gate.
I know.
So NAND gate is actually a combination of AND plus NOT, right? Right? AND plus NOT is NAND gate, right? So what you need to do now, you need to create AND component first, and then create NOT component. Hello? Right?
Yes, I'm still here.
And then wire output of and component to NOT. That's it, right? So what you are doing now, you take each gate by its structure. See here what they have done here. Architecture, start from architecture. Structural is a keyword. It is not a keyword, it is a variable name. You can give any name. Of NAND is, okay, architecture. You start from the architecture. You assume that you already have the entity. Now start from the architecture. There is a signal. What is signal? Can you tell me what is signal?
Signal is wire. Signal
is a wire.
Yeah, that's how I remember. Wire.
And it is capable of it. And I want to name a signal, right? Signal is a keyword and it is a wire. I want to name the wire, and the name of the wire is temp. Okay, hello.
Yeah.
The name of the wire is temp, and it is capable of carrying only 1 bit. That is why I declare bit here. Hello. See here. Bit is a data type. Bit is a data type, and the name is temp. And signal is actually a keyword for representing the wire, right? Now, what I actually define the wire, right? Now the wire is already defined, right? It is declared. Now I want to define the component AND, right? Hello, I'm going to design AND gate. Now I want to start from AND gate. Okay, so what I'm going to do now, I start from the port. The AND gate should have 2 inputs, A1 and A2, right? Each should be, each is actually of bit, right? A1 is 1 bit, A2 is 1 bit, right? Or maybe you can use std underscore logic also, both are same. Hello? Both are same. And output equal to O1 is the output. Out, it is actually a out variable and bit. Okay, you actually this is how you define a component. It is like a entity. See, it is mostly like an entity, right? Hello, this is mostly like an entity, but here you define a component in entity method, and now you got the AND gate, right? Next is what you're trying to do now. I mean, you actually structure the AND gate. You did not define any functionality for this. It is like you are structuring the AND gate. Next, you are going to structure the NOT gate. NOT gate name is invert, and it should have 1 input and 1 output. Input is I1, output is O1, right? So far, with the help of these 6 statements, you define what? You define AND gate and NOT gate, right? Yes or not? Right? AND gate is defined, NOT gate is defined, right? Hello? Right?
Yes.
Now is where you are going to enter into the process. I mean,
so they make the things. The architecture part. They make the things very complicated now. They have to structure everything. You have to list everything. So talk about AND gate, and then you have to talk about NOT gate, and then you have to make sure that all the correct port map has been inserted. So obviously UO and U1, and then this basically 2 things, and then you have to jump into the next part of the architecture. Oh, okay.
right? See what
But
they
so,
do in
but
begin.
but so what you want? So times each other. So that's it. It's a bit not very rigorous, huh? It's not very
Yeah.
rigorous. Do they connect these two together, or it's how this is
That's
gonna
what you're
work?
going to do in begin. What you are doing now, you already define the gates. Now the
Yeah.
time is to map the inputs actually, so that what happens actually, you will be able to bring out the functionality for the NAND gate. See here, U0 is what? What is U0?
Oh, U0 is the AND gate, and then the AND gate need to connect to an inverter. So the output of that will connect to the input inverter. So you get another output.
Yes.
So we output to the input, input to the output. So that's the whole thing. You get what I'm saying? Oh, okay.
Port map. I mean, you are mapping I1 A, I2 B, O1 I. Hello?
Yep. Understood.
You understood this?
Understood.
And
Yes.
next is what you're doing actually. You want to give the output of AND gate to the inverter, right? Hello?
Yeah.
The inverter. That's what you do here. I1 equal to I. O1 equal to Z. I mean, this is not that clear. Let me take some other example for this actually. Wait, sorry.
No, it's okay. So no, it's okay. So next is a multiplexer. I saw the multiplexer.
It's okay. You understand that?
Yes, I should understand that. Yeah.
Okay.
Just now I don't understand. Now I understand. It just needs some time, this kind of things, it takes some time to, fully get into the detail of this. What the F, 60-1, it's straight away a multiplexer.
But before designing this 16:1, we need to focus on how to design 4:1 multiplexer, right? Do you have a code
Okay.
for that?
I
Can you
don't have a code
design
for
that?
Maybe maybe we can Google it how to multiplex. Multiplexer is what was it? MUX is what? MUX is
I have a code. Wait, let me take out that code actually. Multiplexer, this is encoder.
no, this third, this 6. 6 number question 6.
Yes, I think not. Yeah, this is actually the code for
Part A.
4:1 multiplexer. 4:1 multiplexer. Right? Yes. And
Yes.
is the behavior model.
So you made some mistake, you follow his part. You should follow S and W. No put I, W, S, W, and F is output.
Really?
Yeah.
Where is the question? W, no. Yeah, W input, F is output, right?
The F is output, yeah. Wait. No, S,
W,
S is
W,
still, S is okay. S is okay. W is another thing. There are two input.
wait. W is this.
Yes.
Right. And S is this. Right.
F.
Yes. And then this one is F. Right. Yes. So now it works. Yes. This is F. F. This is going to be your W. W, right? Hello?
Yeah, and in a process bracket, you also need to change that to W.
This has to be your W. And now you know the truth table for this, right? Let's start from this one. I think you already have actually. 0 means W0 should be at the output side, right? Right. That's what I do here. If S is 0, then W0 should be at the output side, right? Yes. Else if it is 0, 1, W1 should be at the output side, right?
Yeah.
Else
Yeah. Okay.
Right? No? Yes, right.
Yeah. You're right.
Else, if it is 1, 0, W2 should be at the output side. Right? Right?
Yep.
Otherwise, the other combination that is only left is 1, 1. If it is 1, 1, W3 should be at the output side. Right?
Yeah.
Right? This is quite simple. Right? Yes or no? You understand this?
Yep. Yep.
So you know how to design this for 8:1 multiplexer?
Oh, okay. So
Can you
is
extend
it, is
this?
it whole,
Let's say I want
is
to
it
design this for 8:1. What do you do for this? What should be the change?
8-1.
8:1. Yeah. Now what
How,
should
how
be the
much?
changes? Can you change?
8-1 is there?
Yeah. Can you tell me what changes we should make for this? Actually, 8:1. I mean,
Well,
I
which
will
one?
give
So
you
I'm
the truth table. I will give you the truth table. So it is going to be S2,
yeah.
S1, S0, yes, and F, right?
Okay.
So
Yes. Absolutely.
0, 0.
0, 0.
I mean, wait. Then should go like this. Yes. Now 0, 0, 0 means
1.
W0.
No. W0. Yeah.
0, 0, 1 means W1. 0, 1, 0
Yeah.
means W2. 0, 1, 1, W3.
Yeah. W3. 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1.
W6. 1, 1, 1, W7, right? This is how we should make a truth table for 8:1 multiplexer. Now you need to make changes in the code. Can you do that?
Yep. So basically, so you just I talked to you, change port S 2 down to 0.
Okay. Next.
And then width, so the width is a bit different now. So it's it's not 3 down to 0.
Yes, is 2 down 0, which is perfectly correct. What about W?
Oh, this is why this is still perfectly correct. Can I ask?
Yes, is 2 down 0 means you need 3 inputs 0, 1, 2, right? 0, 1,
Yes,
2.
I understood.
So
How about W?
What about double?
How about W?
You think how many should be there in double? Actually, it is an input. So how many inputs are there? W0, W1, W2, W3 up to W7. So how many?
Oh, I understood.
Now it should be
8.
what? It should be what?
7 down to 0.
Yes.
7.
So totally 8. So 0 to 7. Yes.
Yes.
Now that's it. You're done. Then
Change accordingly. So once 0, 0,
0,
F is W 0.
0, 0, 1.
Yeah, this is 0, 0, 0, 1, and then blah blah blah, and then 0, 1, 0.
That's it. Right? It
And then
should
vice- and then
it
just-
should go with a lot of else if. It should go
And
with
so
a lot
this
of
is-
else if,
and-
right?
And so this is structural modeling.
This is not structure. It is behavior model.
This is behavior model.
This is not structure, right? You are trying to interpret the truth table, right? You are giving
Yep,
the
yep,
real stance.
yep.
Yeah. This is
Yep.
this behavior.
So if I want structural, which is 16 plus 1, that's a different. That's probably for next lesson. Maybe we can do that.
Maybe
or
next session we can.
Maybe I
take.
can.
Yeah.
Yeah. And I mean, maybe I will do it myself, and then I will show you the answer. We'll see.
That would be great.
okay.
But anyway, I have the answer for that also. So maybe we can discuss that if time permits, right?
Yeah.
Right.
Okay. So let me digest this file. Let me digest the A bit, 8 to 1. Let's just wait. So I also want to get to know you, sir. So you're doing PhD, right? Or you are almost done with PhD, or your first year, or
Well, you are asking about my
hello?
degree?
Yeah. I'm curious, very curious.
I did masters in VLSI, very large scale integration.
You did master in where?
I did master in VLSI, very large scale integration. You know the technology VLSI?
Yeah. In which school?
You know, Anna University from India.
China University.
Anna University. We call it one of the reputed university in India, actually, Anna University. I actually did master under Anna University.
Oh, Bana, yes. I heard about that. Yeah. But IIT is for PhD, yeah?
What?
I saw you went to IIT Bombay, or is you're not IIT Bombay?
IIT Madras, actually.
Oh, IIT Madras.
Yes.
For PhD or for
I
what?
mean, yes. I'm doing that. Yes. IIT Madras is actually quite near to my place. It is exactly opposite to Anna University, or actually,
Very stressed, sir. Over there, very stressed. Madras, very stressed.
Madras?
Uh-huh.
I think, yeah, we call it as Madras. Right? You heard about the IIT, right?
I know IIT is very stressed, yes. I think Madras is 10 times stressor than other place.
So, what your native?
Huh?
You are from Australia.
Yes.
I think, did I miss anything here? 011 W3 100, then 101. This is 101. This is
101, you said you missed something.
1110. What about this? This is 11, right? Maybe we can erase this, or we can design like this. Actually, this is also fine.
Okay.
Understand this now? Now, do you think we missed?
Wait, so you made mistake. Definitely made mistake. Why is WF6? Where's W6, yeah? W6.
Oh, right.
W6
right. W6 is for
yeah,
this
mistake.
actually.
0 0 0 0 1 1 0 1 1 1 0 0. So 100 101 110.
Then 111 is not needed, because if nothing falls
I know
under this,
W7. So then definitely wrong. Something wrong, sir. 1 0.
Why?
Where's 1 0?
Why?
F6. Why is it F7? So why is
7 is here.
yeah? Okay, 6.
This is 6 for this.
Why there's no? Oh,
See,
okay. I got confused. Oh, okay. Yeah, I see the thing. Yep.
Otherwise,
LCO.
if you are confused, maybe we can do like this. Else if we can do like this. Else if.
No, just now. I was a bit lost. Yeah, now I understood. Good.
Maybe we can do like this. Now this is quite straightforward, right? This works, right?
Yes, this works as well.
Yeah, that's it.
Right. Very good. Exact 2 hours, sir. We're done for today.
Yeah,
I
I
learned
think
a lot from
we are not clear about structural modeling, right? Maybe if time permits, we will discuss about that. We need to get familiar with that. Designing 16:1 multiplexer with the help of 4:1 is see this is how it should be designed. See, we have already designed 4:1 multiplexer with the help of structural modeling. I mean, what we need to do is we need to create a component for 4:1 multiplexer first. Then we have to make 4:1 multiplexer 4 times to implement 16:1 multiplexer. That's what they have done here. Can you see here? This is actually a 16:1 multiplexer, right? This is actually a 16:1 multiplexer.
So basically, so what they do is that they had 4 to 1, right? 4 to 1, and then they 4 to
4:1, 4:1, 4:1, 4:1 becomes 16:1. That's it.
Yeah. You can also make 32, you know, you just need more, right? You just need 8. You can also do that.
Yeah, we can also do that. We just need to do like this actually. We just need to take 2 4:1 multiplexer to make it 8:1, right? That is also possible.
Okay. Yeah.
Maybe we try that in the next class, I think. Right. Okay,
yeah,
fine.
I think we can do that. We can do that. Thank you, sir. Bye, sir.